Hassan Hilal. He is the professor of theoretical and computational chemistry, King Abdulaziz University. He was a visiting research associate at University of New South Wales, Australia, and State University of New York, Buffalo, New York, USA. He was nominated as a visiting professor at a project of American Chemical Society, Computer-Aided Chemistry Education, Eastern Michigan University. Professor Hilal has many awards. I will call some of them. Egypt Class 1 Max for Science and Arts, Fulbright Fellow, the Egyptian National Science Award, the Contribution to the Science Award, International Science Institute, USA, Cairo University Award for Distinguished Scientific Research, Award for Excellent Scientific Achievement, Chauler, it's French, Chauler maybe,
yes,
for significant contribution to the enrichment of science and cultural from French government. He is a member of many national and international committees. His research interests focus mainly on the application of quantum mechanical chemical methods in the investigation of the electronic structure of molecules. Emphasis was still on the molecules of biological interest, computational methods, techniques, which all these studies reflected in a recent publication which utilizes state-of-the-art methodologies in solving chemical problems of practical interest. His lecture would be on navigation in chemical space towards the structure and dynamic of molecular systems and renewable energy sources, a theoretical perspective. Would you please present your lecture?
Thank you. Bismillah ar-Rahman ar-Rahim. Thank you very much, Chairman. Bismillah ar-Rahman ar-Rahim, walhamdulillah, wassalatu wassalam ala Sayyidi Rasulillah. Our lecture today is just to give you an idea what the computational chemistry group in King Abdulaziz University is doing. We are supporting experimentalists. We are providing answers to some experimental questions, and also we guide experimental questions. I will outline briefly what we can do and what we are doing. And the first thing is we are studying electronic structure. We are studying electronic structure in the sense that all detailed and in-depth structure, type of bonding and characterization, we can obtain it. To do this, state-of-the-art quantum mechanical and quantum dynamical methods are used. In doing this, we encounter some unconventional bonding, the non-covalent bonding, and we explore these also. Acid-base properties can be obtained. Moving from the ground state, we can also investigate excited states. And that's what we will focus today on, excited state chemistry. Excited states completely different, very involving calculation. And we will give two examples of our recent work on the ultra-fast decay and non-adiabatic dynamics of photospectrum simulation. Also, we will show a new trend to predict and calculate X-ray spectrum. Moving to applications, technology is very growing field, and as we saw in the plenary lecture of Professor Naziruddin, solar cells and techniques associated with it is very important and attract a lot of attention. And that's a very active area, not only for experimentalists, but also for theoreticians. So we will give you a hint of something called tautomeric switching. This is for design of molecular switching for signaling devices, memory devices, and for DSC solar cells. That's what we are really doing. But our future perspectives is going toward the hydrogen storage and use of porous material and extended lattice calculation. I will select some examples of our work for each of these areas of applications. First, let us go to the electronic structure of molecules. In the selected example is concentrated on biological molecules, and a disease. Before we start it, I will recall that everything in drugs and treatment of biological chemistry is determined by something called drug-receptor interaction. Drug-receptor interaction is governed by one of fundamental property is the geometry. Geometry is a fundamental property which determine the orientation, the shape of the molecule. These shapes are the way in nature, the way nature tells us how to do it. The enzymes recognize molecules by its shapes. So a lot of properties like these ones, the selective oxidation of enzymes and DNA replication are all depend on the molecular geometry of the molecules. So determining these, determining this the geometry accurately is very important. Not only the geometry, but what we call it as the bioactive conformation. Bioactive conformation is the geometry which will interact with the receptor site. We will take a specific example, Parkinson's disease. What's Parkinson's disease? Parkinson's disease is a very aggressive disorder, results from the decrease of dopamine in the brain. We can't treat the patient with dopamine directly because dopamine do not cross the blood-brain barrier into the brain. So we use this compound. This compound is called levodopa. Levodopa can cross blood-brain barrier and get decarboxylated into the brain, into dopamine. So the treatment is very obvious and easy. No. Because as it can be decarboxylated in the brain, it also can be decarboxylated in any part of the body. Once you orally administrate it, it can be decarboxylated during its passage to the brain. To overcome this, the treatment dose is large. You take a large dose of levodopa to overcome this and get enough dose crossing the blood-brain barrier. But large doses of levodopa causes drastic side effects, very bad side effects. So what scientists did, we want something to inhibit the action of the enzyme decarboxylase. They found this in this compound called carbidopa. As you see, very similar to levodopa, but carbidopa is an inhibitor for decarboxylase. The question is why? Both are having the same skeletal framework, both are aromatic amino acids, having almost the same shapes, but this is decarboxylated and this not. This can cross blood-brain barrier, but this cannot cross blood-brain barrier. The question is why? So this is our task. This is our task. What is the difference? What is structural difference between these two compounds which underlie their activity? We start, as any good start, with the geometry of the molecule. We want to determine the geometry, we want to determine the decarboxylation mechanism, and we want to determine the energies involved in this process. Okay, optimization of the energy of levodopa. The potential energy surface for levodopa is very clear, very well defined, and we could easily obtain the geometry of levodopa. We tried to do the same thing with carbodopa, but we failed. Each time we start an optimization, we get different structure. All structures are very close in energy. Very close, within 3 kilocalorie per mole different energy, but the 3 kilocalorie means about the thermal energy. So molecule can move among these. This is why we call the potential energy surface of carbidopa is flat, and a lot of local minima are there. And once the optimization procedure falls in one of these local minima, you don't have enough energy to overcome the barrier to go to another one. This is not geometry, and this is a common mistake. People doing computation do it. Once they optimize the molecule and got the one optimized structure, they are happy with it and think this is the global structure. No, you can't be sure unless you are sure that this is the lowest energy structure. These are all local minima on the potential energy surface. What we can do then? We went to a more involving calculation, quantum dynamics. Quantum dynamics means we will allow the structure to evolve with time. Now we go into another dimension. We use the time dimension. We got this structure. After 10 femtosecond dynamics, we got this structure, and this structure, as you see, is stabilized with a hydrogen bond. It is much more stable than all other structures, and this hydrogen bond between the carboxyl hydrogen atom and the amino nitrogen would allow the formation of the fetal ion easily, and indeed we calculated the fetal ion for this compound is only 2.675 kilocalorie above the neutral structure. This is an overlay of 35. This is an overlay of 35. This is an overlay of 1,000 structures selected from our 10 femtosecond calculation. And this is just to show you what bonds vibrate and where is the changes are. Now we know the structure. What is the second step? Second step, levodopa and carbidopa are oral drugs. Oral administration of these drugs means you go to stomach. High acidity means with the presence of all these basic centers, you are sure that there will take a protonation will take place. So we examine the protonation of both compounds, levodopa and carbidopa. Protonation of levodopa is typical. Protonation at these negative sites take place, as this is an example, and we did calculate it very easy. But carbidopa show completely different behavior for protonation. Each time we try to protonate carbidopa, we get the same energy, and irrespective of the basic site. Again, we went to a quantum dynamics calculation, and we will see what happens. Something very strange happened, and this underlies the it should work more fast. Now, I will do it myself manually, and this may be better. The proton is approaching the carboxylic group. What happens? It attracts OH, and it took it and it's far. Now look at the bond here, 7-8 bond. Stretch it, and a new bond, 7-9 bond, is formed. So carbidopa is suffering complete geometry change. Not just the loss of the OH from the carboxyl group, The carboxyl group is transformed into carbonyl, and this is NH2, the hydrazine moiety activated with the carbonyl. This is the active moiety, not carbidopa as an amino acid. No, this is the active moiety. This is the active structure. This is a bioactive structure which deactivates the enzyme decarboxylase. And indeed, this enzyme can be deactivated by hydrazines. Now, energetics, very easy then. We can conclude some conclusion like CD is more basic and it will abstract the protons in solution much more efficiently than LED. CD is also more acidic because there is hydrogen that can be lost. Protonation of LED at any and all sites do not cause nor accompanied by geometry deformation. Completely different behavior, although the two drugs are aromatic amino acids. Now, the calculation proceeds smoothly and easily to get all other properties. The decarboxylation, this is the vital process. This is the most important process. What is the mechanism? What is the mechanism for this process? This is the first mechanism we explored. This is stepwise mechanism in two steps to form decarboxylation, carbon dioxide, and the remaining dopamine. And another concerted mechanism has been explored. Also, water-assisted mechanism has been explored. Three mechanisms for decarboxylation of levodopa has been examined, and this is the energetic. In each case, we have determined the transition state, energies and barriers for the transition states, and we were able to calculate the all thermodynamic properties, whether in the gas phase or in solution with several different theoretical models, and compared it with the standard alanine. Alanine has experimentally standard values, so we were able to calculate. This is one example of how we treat biologically important compounds and to get the relation between the structure and their activity. Now we can move to another example of our work, unconventional hydrogen bonding. Hydrogen bonding is known since decades, but hydrogen bonding is known in the context of weak bonding. Weak bonding is like electrostatic or dipolar interactions, all weak van der Waals interactions. But the one we are talking here, the unconventional hydrogen bonding, is hydrogen bonding taking place between ionic species like protonated base and protonated cation and the neutral one. Once you have the hydrogen bond between these two species, you got strong hydrogen. How strong? It is much more stronger than conventional hydrogen bond. It amounts to 35 kilocalories per mole, almost 1/3 that of a covalent bond. So it is really a strong hydrogen bond. Why we are interested in this? Because all ion experiments, all ion injection mass spectrophotometers involve this type of compounds. So we will give an example of hydration of pyrimidine radical cation and the stepwise solvation. This is an experiment done with ion mobility drift mass spectrophotometer, where the protonated pyridine is injected in a vapor with helium water mixture. Of course, all experimental conditions are adjusted. We don't do this experiment, but our colleagues in Virginia Commonwealth University did. And this is what they obtained, the mass spectrophotometers, and they can assign these bands. But they don't know what happened. That's what we tried to do. We tried to do this. we want try to identify and characterize each of the water protonated pyrimidine interactions and calculate the binding energy and predict this relative stability, and to identify the origin and of these energy, stabilization energy, and characterize the new bond, the unconventional hydrogen bond here. Indeed, we did that. This is protonated pyridine, and this is water molecule. We studied one water molecule, 2 and 3 water molecule interactions with the pyridine. Each time we calculated the geometry, orientation, and binding energy, and identified the presence of the strong ionic hydrogen bond between the pyrimidine and the water along the hydrogen bond. And also we predicted the possibility of existence of a chain hydrogen bond. A chain hydrogen bond with the addition of more water molecules like this, but the strength of the hydrogen bond decreases as the chain length increases. This study is extended to other solvation, solvation with other solvents, not water, with methanol and with acetonitrile. And this is the result for this calculation. Very sensitive, because as you see here, the energy values here is very small, of the order of 8, 7, 12, 15, and so on. The energy being that means you are sorry, the total energy of the molecule is about hundreds. And with this small 100 atomic units means thousands of kilocalories per mole. So any error in the calculation would give you very bad results. And that's why the calculation of unconventional hydrogen bond, of non-covalent bonding in general, needs very high and exact calculation. You need very involving calculation to reach reliable values of binding energy. Okay, let us leave the bound state alone now and jump into the excited state. Excited state is a completely different story. Very difficult to calculate because in general, lifetime of excited state is very short. Very short, so you are doing everything in very short time. And you want to explore. There is no local minimum to fall in it and calculate it. I will give 2 examples of our work on the excited state. The first one is the photostability, photodamage problem of DNA bases. And this is a vital point to understand. And the other one is the calculation and simulation of LH X-ray spectroscopy. Okay, let us take the first example. What happens? What happens if UV light with UV radiation fall on the skin of our hands, for example? It may be absorbed by the DNA bases, which get excited. Get excited, the excitation may disrupt the strength, cause some burns, and in some cases, cause skin cancer. Because mutation takes place, chemical change in the structure. This is a very important problem, of course. This is vital. What happened? What happened? I just posted this on my account on Facebook, asking you, everybody, can you imagine how many photos of light fall on your hand in 1 second? Any one of you think or thought about this? Salam, you are from Canada and you should think of this because you are looking for sun. No. In one sunny day, about 500,000 photons fall on your hand in 1 second. Any one of these photons is capable of doing this. But alhamdulillah, this is not the case. Skin cancer is very rare and do not happen quite often. So there should be a mechanism. ربنا سبحانه وتعالى خلق mechanism to dissipate this excitation energy. How this happens, this is up to us to discover this mechanism and to contribute to this understanding. So the problem is, how can the excited molecule get rid of the excitation energy and return back to the ground state in the same, exactly in the same geometry, exactly in the same structure, not in other structure. These questions, scientists in the last 10 years asked themselves, what happens when molecule get excited? How does it relax and get rid of the excess energy? How long the process is? You will discover that the time here is very important. What is the product of this excitation? And how does the relaxation affect or is affected by the environment? And a very important question, can we interfere? Can we interfere and control the outcome? This is what we will try to do. Let us see, this is a typical, these are two potential surfaces. This is the ground state potential surface in yellow, and this is the excited state potential energy surface in red. And this is a molecule vibrating. The molecule in general vibrating in the ground state all the time, and when it absorbs a photon, it will get excited to the excited state, will stay very short time and return back to the ground state. This is the fluorescence. This is the absorption and the emission, normal absorption and emission. The time span here is nanosecond. Let us now go to something like this. These are the same two potential energy surfaces again, but the relation between them is different. There is something called avoided crossing here. They close to each other, very close to each other. The molecule still doing the same vibration, absorbs a photon and gets excited to the high. But now it falls into another minimum. This happens, and this is biochemistry. And the molecule is trapped here, and this is very dangerous. If this is a DNA molecule base, then we are in trouble. Okay. Which reaction path will a DNA molecule take? And we will look at this again and see this is easy. This is a photochemical process where the molecule can overcome a small barrier here and fall into this minimum, and where all photochemical reactions can take place. Even without crossing here, even without touching between the two surfaces. Now, this is photophysical. The photophysical, the molecule doing this, look at this, because here it is very important. The molecule return, although the potential energy surface relation, this is rahmah min Rabbina subhanahu wa ta'ala. This is called conical intersection. This is conical intersection, the intersection between the two surfaces, which ensure to return back to the original, not the other minimum. This is what Rabbina subhanahu wa ta'ala created for all DNA bases. All DNA bases contain the relation between the ground and the excited surface. So you have intersection here called conical intersection. Conical because you have two cones touch each other and this like this. Something like that. Here actually the figure show as if they touch in a point. No, they touch on, because they are two multi-dimensional surfaces, they touch in several points on a stem. And there are several pathways to dissipate the energy, and the excited molecule funnel directly to the ground state. If you remember the time scale, it happens in femtosecond time scale. There is not enough time to harm the skin or harm anything. So it funnels directly. This is the all molecules. Every one of the DNA bases had its conical intersection. We try to calculate for cytosine. We contributed to the understanding of the conical intersection in cytosine, and we calculated two conical intersections. One SOFA type. This is what SOFA is turned upside down. And this is called a twisted structure. We determined all the branching vectors, and we did calculate the potential energy surface for these two. But the energetics is very easy. The energy difference between the two structures is very small, and they cross over the same barrier and almost have the same lifetime of 0.2 picosecond. Experimentally, the cytosine excited state show two different lifetimes. So there should be another busway, a third one, or more than two other busways for cytosine. We continue doing calculation. This man did an experimental electronic spectra for cytosine and determined lifetime of excited state, one at 0.2 picosecond and the other at 3 picosecond. So we continue doing this, but we carried out something called CAS-SCF, Complete Active Space, SCF calculation, multi-configuration interaction, and in this case, this is very involving calculation because what you do, you calculate the ground state and the excited state energies with one criterion. You are looking for the point at which the two states have the same energy. This is the criteria. So you are searching in a multi-dimensional space for this point. All techniques has been used, and finally we got another third conical intersection. We called it semi-planar conical intersection, and we determined its energy, its lifetime, and all the branching spaces which identify it. So this is, I think, a good contribution from our group to the understanding of how cytosine dissipate the excitation energy. LH X-ray spectroscopy. We usually we are far from X-ray. LH means excitation of core electrons, B electrons, to the vacant shell. This is very difficult because usually we work with something like this, frontier orbitals. Frontier orbital can get excited easily, and we can calculate this. But now you want to do something like this. You want to excite electrons from deep inner electrons, orbitals, to the vacant. This will be very involving. If I take I use the same techniques here, means the CI matrix will contain hundreds of molecular orbitals. And this is out of the computational limits. So we came up with, in cooperation with our colleagues in Rostock University in Germany, with a technique to calculate the orbitals and then replace them, take them to the frontier site, and then they calculate the spectrum. This we used as prototype manganese complexes, which are used for the oxidation of water, and did that for calculate the spectra. These are the selected orbitals which were taken in the active space, and these are the correspondence between experiment and theory. Let us go to application technology. Now technology, quantum chemistry is going to technology, and we are going to talk a little bit, and very fast, something called molecular switching and signaling devices. This is the switch. On, off. This is mechanical switch. But now nobody uses this. Everything is now going to digital. What's mean digital? Everything, even the counters, digital. Our clocks, watches, is digital. Digital means you use this. Binary numbers, 0, 1. 0 on, 1 off. And combination of them created complete different language. The memory of the computer, the memory, when you say 4 giga, 8 giga, and so on, nothing except collection of these. So we have molecules which can do this. Molecules which can well define the state by external stimuli can move to another well-defined state. Cis, trans, enol, keto. So this is what chemists discovered, that I have already on-off. I have 0 and 1. Let us call this 0, then this 1. This is, if you can have two well-defined states and reversible change from one to the other state, then you have a molecular switch. What is the advantage? If you have 2 grams of water, 5 grams, you have millions of these molecular switches. So you have millions of memory chips if you can do this. This is a very recent but growing field, and people are trying very much to apply. Now the fact is, this is right, but how can we use it? Very recently, applications of the idea of molecular switch in biology and nanotechnology became real in market. We will talk about our contribution to this problem. Antonov, this is a scientist in Germany, suggested that we can use all our wealth of tautomers and created switches based on the idea of tautomers. And he suggested the use of this one. He found that this one can be used. This is 1,4 hydroxyformal naphthalide. 1,4 hydroxyformal naphthalide. The problem is, he said it can be converted into the keto form, and no one in the organic chemistry knows how this can be done directly. Several different routes have been suggested, and we contributed to the understanding of this tautomerism by suggesting 2 routes. Route 1, through the excited state. Hydroxynaphthols is aromatic. Aromatic alcohols like phenols have a property called photoacids. Photoacids mean when they get excited, they acquire abnormally high acidity. Means it can be, the hydrogen of the OH can be ionized very easily. Now, how can this done on a conical intersection again? So the photoacidity and tautomerism can take place on the excited state potential energy surface and 40. This is the first idea, this first route, and this needs a lot of quantum dynamics simulation. It is working, and we don't reach yet any conclusion. The other way is we have examined all the structural features of this compound and the other tautomer, and we came up with the idea of dimerization. This compound can form dimers, either head-to-head, head-to-tail, or stacked dimers. These are stable dimers, and this is the most stable one. Okay, how can this contribute to tautomerism? Look at this. This is the stacked dimer, and you see here, this is how the proton can transfer to form the keto form. Okay, this is a lot of conclusions. I will not stop here. This is another molecular switch, which we are proud of doing it. This is very known tautomeraze, chip-based, 2-hydroxy chip-based tautomeraze, but we were trying to see the effect of substitution on the position of this tautomeraze and the rate of tautomeraze. This is very involving statistical thermodynamic calculation, where we calculated all the statistical factors and all thermodynamic factors for the tautomeraze. And we examined also effect of solvent and substituents. Okay, I will not detail the how you have we have still, Mr. Chairman. Do you still have time? Or? Okay, the plenary lecture, Professor Naziruddin was talking about solar cells. We are contributing to the understanding of solar cells, but theoretically. This is what you were talking about. We did a lot of calculation because the problem is homo-LOMO gaps of the dye. This is a solar cell, mesoporous titanium oxide semiconductor, and this is a counter electrode, and this is electrolyte. In the electrolyte, there is a dye. The problem starts with the excitation of the dye. Once the dye absorbs light, it gets excited, an electron in the LOMO, instead of returning back to the HOMO and get recombination, it is injected into the mesoporous film and in the outer circuit to the counter electron. So you create a current. You created current. This is the idea of the solar cell, the dyes inside solar cell. All the thing is to play with this thing. How to make the injection here, driving for much work is to rise LOMO. How to make the recombination, very difficult by lowering the HOMO. How to make the harvesting to absorb as much radiation as possible. This is what we're doing. A lot of calculation, sometimes positive, sometimes it's not very efficient, but anyway, we try some very typical dyes, and this dye, for example, is typical with a 12% efficiency, but substitution didn't increase the harvesting efficiency of this dye much. But this is not always the case. We have other dyes here where we could shift the absorption toward red and have more harvesting of the light. And of course, all cell parameters can be computed. This is what Dr. Anwar here, Dr. Shaban is working with, new acceptors based on Indene C60. And these are very complicated calculations, of course, but he's still doing it with 1, 2, and 3 Indene substituted C60 molecules, which are very efficient electron acceptor. We want to examine also the absorption on the titanium oxide mesoporous surface, whether the absorption is physical or chemical, and there is a lot to do. At the end, I would like very much to thank the computational chemistry group, our colleague in the chemistry department, Dr. Abdurrahman Al-Yubi, Dr. Saadallah, Dr. Shaban, Dr. Osman, Dr. Noha Wazan, and our students, now Dr. Aisha Al-Amri, Basma, Ghadir, Rawan, Safiya, and finally Fayaz, and our cooperators groups. We are cooperating with groups all over the world. Professor Jean-Luc Brida's group in Georgia Tech, Professor Oliver Cohn in Rostock, Professor Sam Michel in Virginia, and Professor Mario Rubati in Madison Banking Institute. I would like to thank you all for your patience and for listening to me.
Thank you very much, Professor Hilal, for the interesting lecture. Since we are well behind the schedule, we have probably 1 or 2 questions. Yes, please.
Just one small question about the energy of DNA.
Energy of?
Yeah. The energy of DNA molecules is that you said that there is 2 minima.
CD in the first thing?
Yeah, for the effect of UV on the DNA.
Ah,
There is two minima for the between excited state and the ground state. These two minima. What is the conflict of these two minima on the structure of the DNA itself? These two minima means destructions or denaturations of DNA.
First of all, the example given here on the relation between excited and ground state is a general example. Ground state, potential energy surface, or any potential energy surface is multidimensional with local minima, many local minima. One of them is global, lower energy, and the other exists as local minima. So if excitation take you into one of these local minima, you are trapped. This is either protomer, or isomer, or enantiomer of the same compound. If this happens with the DNA basis, you are not you, anybody will be in a very bad trouble because this is mutation. This is mutation, and the strand will be disrupted, and all kinds of things will. Yes, there is always another minimum, but the problem is whether you will fall in it or not.
One short question, please. Yes. Okay.
Really, your lecture is very gratifying, not good only, but just I have to inquire. The first is, I think you did your calculations about the hydrogen bonding in solid state or in solution?
In solution in gas phase action, because it is injection of protonated pyrimidine in the water, in helium water vapor. It is injection in the gas phase.
But excuse me, why you did forget you can get the proton transfer, not hydrogen bonding in solution? You can get this.
Yes, because the experiment is mass spectrum. Yes, is mass spectrum, ion mobility, drift, and in the spectrum obtained there is no complete transfer. There is bulk molecule. The mass is obtained equivalent to the mass of one protonated pyridine plus water, or 2 or 3. The problem is how they are bind, not what is the species. The species is determined experimentally already. But how it is bind and what is the strength of binding, that's what we were contributing to.
Yeah, the second is, you, as you, sorry,
It's okay, but it's
not more 1 minute. When we expose our skin to the sunlight, you study the effective UV radiation on our skin and will take disruption for the DNA and so on. Why you did study the effect of IR radiation?
Yes. IR radiation means heating effect.
Yes.
Means you heat your
Yes.
skin. And this will not excite or do anything to the DNA base. It will not change it. It will burn your skin.
Yeah, thermal
But,
effect.
yes, thermal effect.
Yeah.
And the thermal reaction taking place for any DNA basis, it will not mutate. It will not change its structure. It can be destroyed, but cannot be changed into another.
Yeah.
But the photochemical reaction is very dangerous. That's what we are focused on.
Yeah, photochemical happened only with UV.
Yes.
Thank you.
I
think-
will not excite.
Yeah.
I think we should stop the discussion. If you have further questions during the lunchtime, you may ask. Please join me to thank Professor Hilal once more. We now move to the short oral presentations. The first presenter is from Egypt, Anwar Said Mohammed Al-Shawi. The title of his presentation would be Paracetamol Drug and its Carcinogenic Effect. Please present your lecture and keep the time as well as possible.
Welcome overall. Assalamu alaikum wa rahmatullahi wa barakatuh. نعم. Please عايز اغير الصفحة. هيبقى هنا. Okay. Products of modified paracetamol and alternative of paracetamol. Anwar El-Shahawi from Asyut University, Safa Kasti from Abdulaziz, King Abdulaziz University. She works in comet assay, and Hana Gashlan, she works in nephrotoxicity. Anwar El-Shahawi works in quantum spectroscopic studies. Paracetamol has many names: acetaminophen, acetylaminophenol, 4-hydroxyacetylenide, and it has worldwide use as analgesic antipyretic medication that is readily absorbed after administration and has side effects and toxicity even when used in recommended dose. Paracetamol toxicity is caused by excessive use or overdose of the analgesic drug paracetamol called acetaminophen in the United States, mainly causing liver injury. Paracetamol toxicity is one of the most common causes of poisoning worldwide. In the United States and the United Kingdom, it is the most common cause of acute liver failure. This is the structure of the paracetamol molecule. It has transform in which the amino hydrogen atom and the carbonyl oxygen atom have different orientation, but in this form, the amino hydrogen and carbonyl oxygen have the same orientation or the same direction. Paracetamol molecule is metabolized mainly in the liver into toxic and non-toxic products. Three metabolic pathways are notable in the following figure. The hepatic enzymes system metabolize paracetamol, forming the toxic product as NAPKI, N-acetyl-para-benzoquinone, imine, or N-acetyl-imidoquinone, which is symbolized by MBA, metabolite paracetamol. For simplicity, all three pathways yield final products that are inactive, non-toxic, and eventually exerted by the kidney. In the third pathway, however, the intermediate product, the metabolized paracetamol, is toxic. This means that metabolized paracetamol is the mainly responsible for toxic effect of paracetamol. This figure explains the pathways of metabolism of paracetamol in the kidney. The first two pathways are safe: glucuronidation, the second, sulfation, the third, in which the NAPKI is formed, N-acetyl-para-benzoquinone imine, which alters to safe product in presence of glutathione. This is general metabolism scheme for phenacetin and paracetamol. All of them alters finally in the liver to NAPKI, N-acetyl-para-benzoquinone, which is injury or harmful for the liver. FDA and paracetamol. Recommendations as of October 2010, in June 2009, an FDA advisory committee recommended that new restrictions should be placed on paracetamol usage in the United States to help protect people from the potential toxic effects. The maximum dosage to be consumed at any given time would be decreased from 1,000 milligram to 650 milligram, while combinations of paracetamol and narcotic analgesics would be prohibited. Committee members were particularly concerned by the fact that the present maximum dosage of the paracetamol had been shown to produce alterations in the hepatic function. The first molecule is phenacetin, which is very similar or has structural resemblance with paracetamol. In the para position, you see it has ethoxyl group, but in the paracetamol molecule, it has hydroxyl group, which is para-hydroxyacetalide, finally to produce NAPKI or N-acetyl parabenzoquinone imine in the metabolism. FDA and phenacetin. We know from the previous structures, phenacetin is mainly the same paracetamol molecule, but FDA, with respect to phenacetin, is a pain relieving and fever reducing drug widely used from its introduction in 1887 until banned in the United States by FDA in 1983. Its use has declined because of its adverse effects, which include increased risk of certain cancers and kidney damage. It is metabolized to paracetamol, which replaced it in some over-the-counter medication following the ban on the phenacetin. All of these kind of molecules have the trans and cis form and ISP I talked before in this aspect. Side effects of paracetamol. Liver damage due to paracetamol, anadine, Panadol, Calpol. Panadol, paracetamol, cetamol, any of the products in the pharmacy. Acute overdose of the paracetamol can cause potentially fatal liver damage. According to USA Food and Drug Administration, acetaminophen can cause serious liver damage if more than directed is used. And in 2011, the FDA required the manufacturers to update labels of all prescriptions combination acetaminophen products to warn of the potential risk of the severe liver injury, and launched a public education program to help consumers avoid overdose. The risk may be heightened by frequent consumption of alcohol. Paracetamol toxicity is the foremost cause of the acute liver failure in the Western world and accounts for most drug overdoses in the United States, the United Kingdom, Australia, and New Zealand. According to the FDA in the United States, there were 58,000 emergency room visits, 26,000 hospitalizations, and 458 deaths per year related to the acetaminophen associated overdose in the 1990s. Within these estimates, unintentional acetaminophen overdose accounted for nearly 25% of the emergency department visit, 10% of the hospitalization, and 25% of the deaths. Paracetamol is metabolized by the liver and is hepatic toxic. The hepatic toxic side effects are multiplied when combined with alcohol drinks and are very likely in chronic alcoholics or patients with liver damage. Some studies have suggested the possibility of moderately increased risk of the upper gastrointestinal complications such as stomach bleeding when high doses are taken chronically. Kidney damage is seen in rare cases, most commonly in the overdose. The Food and Drug Administration has warned doctors against prescribing paracetamol narcotic combinations whose dosage exceed 325 milligram of paracetamol due to hepatotoxicity risks of greater magnitude than the therapeutic benefits conferred. Skin reaction. On August 2, 2013, the U.S. Food and Drug Administration, FDA, issued a new warning about paracetamol. It stated that the drug could cause rare and possibly fatal skin reactions such as Stevens-Johnson syndrome and toxic epidermal necrosis. Prescription strength products will be required to carry a warning label about skin reactions, and the FDA has urged manufacturers to do the same with over-the-counter products. Asthma. There is an association between paracetamol use and asthma, but the evidence suggests that the likely reflects confounders rather than a causal role. A 2014 review found that among children, the association disappeared when respiratory infections were taken into account. As of 2014, the American Academy of Pediatrics and the National Institute for Health and Care Excellence continue to recommend paracetamol for pain and discomfort in the children, but some experts have recommended that paracetamol used by children with asthma or at risk for asthma should be avoided. Paracetamol use and risk of ovarian cancer. I don't talk in this object. Charge transfer. Even paracetamol has many side effects, but in the literature it is called painkiller. Therefore, all of the patients take paracetamol. Charge transfer studies or electron transfer studies. The comparative studies between paracetamol and the metabolized paracetamol in the human being liver by the quantum mechanical density functional theory, DFT theory, finds out the strong carcinogenic power of this product. As well, these studies have been extended over different derivatives of acetanilides. Of course, paracetamol is one of the most important derivative of acetanilide molecule, such as the two conformances and trans of para-nitroacetanilide. This is an example of resemblance between this molecule and paracetamol, and para-bromoacetanilide, which have good resemblance or structural resemblance between paracetamol molecule. Also, it is necessary to compare the study of paracetamol with what of phenacetin. Phenacetin also very close molecule to paracetamol. drug. Dealing with a molecule lies between paracetamol with aspirin and thioaspirin. It has been concerned with N-acetyl anthranilic acid, which has resemblance between aspirin and paracetamol. Therefore, I suggest that this molecule can be used as alternative of aspirin and paracetamol. Alternatives of paracetamol. These are molecules which can be used as alternative drug of paracetamol itself. Because parabromo acetanilide, of course, it has no chance to form N-acetyl parabenzoquinoamine because the para position is blocked by the bromine atom. In the N-acetyl anthranilic acid molecule, the ortho position is occupied by carboxyl group, therefore it has no chance to have the quinoid structure, as the same as thioaspirin. What is the mean of cancer? Cancer. To deepen the denotation of cancer, it is mutual electron transfer between the nucleic acid bases in the nucleus and the electron donor or electron acceptor. That is to say, free radical, drugs, even some food like grease and freeze. The electron transfer energy in the CT complex between donor and acceptor, cation and anions, was calculated according to the following equation. ECT, this is the energy of electron transfer between donor and acceptor. ID is the ionization potential of the donor. EA is the electron affinity of the acceptor. C plus and C minus the potential energy or coulombic potential energy of the anion and the cation. The coulombic potential energy can be calculated by this equation. التكة فين؟ Yes. Wait please 5 minutes. ايوه عايز اشاور على المعادله. الاحمر بتاعها فين؟ الله 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 انت لخبطت لي الدنيا. فين بقى ارجع كمان. كمان. ايوه هنا. فين بقى الاحمر؟
Pointer is here.
Pointer. Please. هنا. This equation for calculation of the electron transfer between the donor and acceptor. Where I said before, all of these are, I explained before. So, these molecules, this nucleic acid bases, adenine, guanine, uracil, cytosine. These are the total energy in atomic unit, ionization potential, electron affinity. EA is electron affinity in electron volt also. Ionization potential deals with the oxidation of the molecule. Electron affinity deals with reduction or the ability of the molecule to receive an electron. Paracetamol compound, phenacetin, metabolite paracetamol here. Has metabolite paracetamol, N-acetyl parabenzoquinoamine, which is very injurious for the liver. You see the electron affinity of this molecule is very high with respect to nucleic acid bases. Therefore, this molecule withdraws an electron from nucleic acid bases to produce cancer in the liver cell. These studies concerned the charge transfer energy of these molecules with nucleic acid bases to conclude the carcinogenic character of the studied molecules or drugs via the charge transfer energy values. The charge transfer energy can be illustrated as cancer energy barrier. Cancer energy barrier is a new term introduced to the drug to know which drug is carcinogenic or non-carcinogenic. Acceptors and the donor can be defined by the relative values of the two molecules. The molecule having higher electron affinity acts as acceptor to form an anion in the CT complex. The molecule having lower electron affinity and lower ionization potential acts as donor to form the cation in the CT complex. The electron affinity and ionization potential have been calculated from DFT, density functional theory method using Gaussian 03 program. Here, king of calculation, Dr. Hassan Hilal. Since the electron affinities of paracetamol, phenacetin, and parabromoacetylide are lower than those of nucleic acid bases, therefore they act as donor to produce charge transfer complex in which these molecules are cations and the nucleic acid bases are anions. But metabolite paracetamol or N-acetyl parabenzoquinone or paranitroacetamide or N-acetyl anthranilic acid or aspirin or thioaspirin have electron affinity larger than those of nucleic acid bases, therefore they act as acceptor to be in the anionic form in the CT complex with the nucleic acid bases in the human being nucleus to render the cell behaves abnormally, which is that's to say carcinogenic or cancer effect. The cancer energy barrier of the studied compound with nucleic acid bases. Here we see the electron transfer energy very, very low with respect to metabolite paracetamol. This means that there is spontaneous electron donor from guanine to metabolite paracetamol to produce carcinogenic cell. All of course, the other molecules have yes, I do. I did. Okay. About 3 minutes. So, all the molecules which have large electron transfer energy, they are safe from cancer effect, like parabromoacetylide. Even paracetamol itself as a molecule is safe, but the metabolite, its metabolite product is very harmful for the liver. Also, aspirin is very reasonable, not has appreciable value of electron transfer and is far from cancer effect, as well as thioaspirin and N-acetyl parabenzoquinone. The most safe product of this molecule from cancer effect is parabromoacetylide. From the previous charge transfer energies, it can be concluded that the metabolized paracetamol has the lowest energy transfer, indicating to the easiest withdrawing of the electron from guanine. The cancer energy barrier between metabolite paracetamol and the nucleic acid bases is small in general, especially with guanine as shown before. The charge transfer energy can be illustrated as the cancer energy barrier whenever it has large value. This means that the safety of the drug from the cancer or carcinogenic effect. For example, parabromoacetylide in the previous table has charge transfer energies with the nucleic acid bases among 4 and 4.6 electron volt. This means that the strong safety of this drug with respect to cancer effect. On the other hand, from the previous table, it is shown that the cancer energy barrier of metabolite paracetamol is very small, 0.4 electron volt, which is very, very, very small, and produce spontaneous electron donor from guanine to metabolite paracetamol. Spontaneous electron donor from guanine to metabolite paracetamol to produce ionic nucleus, hence the cell behaves abnormally, which is known as cancer. This is the mean of cancer. I deal now with glutathione. Glutathione is right defense immunity in the liver from Allah to protect liver from this injury metabolite paracetamol. Because there is proton transfer between glutathione and this product to produce more safe product. The existence of the glutathione in the liver alters NABKI or metabolite paracetamol to a safe product by proton transfer. The frequent usage of the overdose paracetamol consumed glutathione in the liver, I repeat this, the frequent use when you have headache, when you have tooth pain, when you have any pain in your body, you take paracetamol. The frequent usage of the overdose of paracetamol consumes the glutathione in the liver. Hence, after formation of paracetamol, of metabolite paracetamol, NABKI, in the absence of glutathione, withdraw directly from electron from the nucleus of the liver. Hence, the nucleus behaves abnormally and cancer exists. So, this explains why the cancer effect does not appear immediately after administration of paracetamol drug. Therefore, the liver cancer will appear after consumption of glutathione due to your continuous usage of paracetamol for your pain in every part in your body. Conclusion. Phenacetin and paracetamol, they are very close molecules, are safe after avoiding the formation of metabolite paracetamol by addition of transferable proton compound such as glutathione. Of course, glutathione cannot be used in the drug because it can be digested during administration, after administration. Paracetamol complex are safer than paracetamol. Paracetamol complexes are safer than paracetamol itself, as well as phenacetin. 3, it is advisable to use parabromoacinide as a drug instead of paracetamol, since it has very high electron transfer. N-acetyl alpha-linoleic acid compound can be used safely as alternative drug instead of paracetamol and aspirin. Thank you for your patience and your attention. Okay.
Thank you very much. I think we have no time. We have 3 more lectures. Therefore, if you have any question, please discuss with him during the lunchtime. So we move to next speaker, Yunus Umar from Saudi Arabia. His lecture will be triple-tailed hydrophobic monomer for the synthesis of amphiphilic polymers based on dealinated ammonium salt. Would you please present your lecture?
Okay, assalamu alaikum. Good afternoon. I'm Yunus Umar from Jubel Industrial College. I will be presenting on triple-tail hydrophobic monomer for the synthesis of amphiphilic polymers.
Would you speak to the microphone?
My presentation will be outlined as follows. I will be talking about So I'll be talking about introduction and then move to polymerization techniques, and then we'll talk about Butler cyclopolymerization. I'll also talk about objective of these particular studies. We'll also be talking about the synthesis of the triple tail monomer, and then the polymers, and then the characterization method that is being used, and then we'll talk about resultant discussion, and then finally the conclusion. Associating polymers generally contain small amount of hydrophobe within hydrophobic chain. These hydrophobes could be randomly distributed as indicated in red, or they could be in form of a block, or they could be in form of a telechylic polymer at the end of the polymer chain. Now what happens to this is whenever these polymers are dissolved in aqueous medium, there is possibility of having a large molecular aggregation because of association, or this will lead to large viscosity, and it will lead to also shear thinning behavior, and in most cases they have the ability to store and release hydrophobic moiety. Now another possibility is to have intramolecular association within the polymer chain. They undergo intramolecular association leading to a small apparent size, low viscosity, anomalous shear response, and ability to store and release energy. But our main interest is the first one, which is intermolecular association. Another possibility is you could also observe no association at all. Now, generally, to form associating polymers are usually formed by micellar polymerization, and a typical example of that is the solution polymerization of acrylamide, which requires just 3% of the monomer with few percent of the hydrophobe to form microbulk polymers. Now, this is a typical representation of micellar polymerization. The polymerization is initiated in aqueous medium, and the hydrophobes are trapped in a micelle. So as the polymerization continues, it eats the micelles, and then the the hydrophobes generated in form of blocks, which are represented as white hydrophobes. But this type of polymerization is not available for our system. So what happens is when you have a block arrangement of the hydrophobes within the polymer chain, in aqueous solution, these chains can associate together to form a network, and this network can lead to high hydrodynamic volume and increase in viscosity. And this is our main interest. Now, when you look at the other side is intramolecular association. The hydrophobes will interact with each other intramolecularly, leading to a smaller volume of the polymers. Now, what happens generally is if you try to plot the reduced viscosity against concentration of the polymer, for a normal polymer you get a straight line, but for the hydrophobic association at certain concentration called critical hydrophobic association concentration, the viscosity will increase tremendously because of the hydrophobic interaction within the aqueous medium. And this is what we represented as the critical association concentration. Now, these polymers are usually used in so many applications like enhanced oil recovery. They are also used for water treatment. They are also used for cosmetic formulations, drug delivery system, rheology modifiers, and sometimes in protein separation, and in most cases where effective viscosification is of interest. In our system, we have diallyl monomer. These monomers, the Butler was trying to synthesize a polymer that will be used as an ion exchanger. So he used diallyl monomer to get this particular polymer with a residual double bond. But what he observed, so that this polymer can be used for ion exchange resin application, but what he observed, instead he got water-soluble polymer. Now, to explain this observation, the monomer undergo a free radical polymerization, addition polymerization, in which the free radical attack one of the double bond to form a secondary free radical. It was initially thought that the next step is intramolecular cyclization to form 6-member ring, which is the most thermodynamic stable free radical. But subsequent studies discover that it undergo a kinetic intermediate, which is primary free radical. And since that time, a lot of polymers in these areas were produced, and this is one of them. With different R groups were synthesized, and sometimes these polymers were copolymerized with sulfur dioxide to form a copolymer, and sometimes a group of scientists also try to use these monomers, which I call monomer 1, to copolymerize them with hydrophobic monomer. And here, they got critical hydrophobic association concentration at 16 to 17% of the polymer, which is too much compared to the acrylamide system. The second group also tried to attempt to use that particular monomer, and they got almost the same thing, 16 to 17. And another group used copolymerized M1 with that M2 with 5 to 30% mole, and they discovered that it can lead to a polymer with intramolecular association. Therefore, we try to synthesize a monomer that will look like a macro block so that we can achieve association at a very low concentration. So our objective is to design and synthesize a novel hydrophobic monomer that will result in a low critical association concentration. We also design a novel monomer that will have micro bulk in nature, which are called triple-tailed. And we also have the monomer that is, the polymer that is pH responsive, that is ionic polymer, which we can either make it a cation or anion. And then we also characterize these polymers using different characterization techniques. And we also investigate the viscosity behavior of these particular polymers. Now we use the following characterization method: NMR mainly to determine the hydrophobic content and also for structural elucidation. We also we use FTIR for structural elucidation, capillary viscometry for intrinsic viscosity measurement, Brookfield for viscosity at different shear rate, and then we determine the molecular weight, MW, and the radius of gyration, and second variant coefficient using static light scattering. And then we use constant strain rheometer for dynamic viscosity. Now, this is a typical example of micellar system where you have an hydrophobe with 3%, but in this case, for you to have, the kinetics have shown that for you to have a meaningful polymerization, the percentage must be from 50 to 60%. So we cannot use micellar polymerization. So we decided to synthesize this particular monomer, a triple-tail monomer, so that we represent it as a triple-tail, but to have a meaningful assessment of what we are doing, we decided to synthesize a double-tail, a polymer for comparison, and of course, we also synthesize a single-tail for comparison. So what we do is to keep all these monomers. These are the 3 monomers: triple-tail, double-tail, and single-tail. But we try to keep the concentration the same. For example, we have 8 moles of that is equivalent to 4 moles of double-tail, and it's equivalent to 2.67 moles of triple-tail, just to have a meaningful assessment of the hydrophobic properties of these polymers. We also synthesize another set, 12 moles of single, 6 moles of double, and 4 moles of triple. They all contain the same moles of the hydrophobe, but of course differently arranged. So we also have the next one. The first one we couldn't because it's insoluble in water, and we take the double tail, which is 8 moles, and then the triple tail, which is 5.33 moles. So in order to investigate this exciting proposition, we decided to synthesize this particular monomer. The triple tail, we start with gallic acid, which is treated with equivalent 4 mole equivalent of sodium hydroxide and bromo-octane, and then subsequently treated with sodium hydroxide and then hydrolyzed to get trioctaloxy benzoic acid, which is converted into acid chloride using thionyl chloride and subsequent reaction with diamine to give amide. The amide is undergo reduction followed by acid hydrolysis to form an amine, and then we protonate the amine so that it will be water soluble. So this is our monomer. All the compounds were isolated, purified, and characterized. For example, now this is the polymerization. That is our hydrophobe in yellow, and then we'll have the hydrophilic monomer copolymerized with SO2 to form a polymer. This our polymer, we call it cationic polyelectrolyte because it contains a cation and is water soluble. This is a typical IR of the first compound, which is trioctaloxy benzoic acid, the first one, and then the second one is the simulated NMR of the compound, which matches very well. And we were able to account for each and every proton. This is for the amine. The first one, the top one is the experimental one, and the second one is the simulated, which matches very well with our structure. This is for the monomer, the NMR of the monomer, and the down one is the simulated type, and each proton is accounted for. We also do elemental analysis. We also do IR analysis, but this is just typical examples. This is the NMR spectra of the polymer. The first one is just hydrophilic without hydrophobe. The second one is contain twin tail, double tail, and then the last one is a triple tail of the polymer. Each one is characterized with NMR, elemental analysis, and molecular weight characterization using light scattering. Now, this is a typical viscosity behavior. For the one, we have the green one, the M0 means we want no hydrophobe. So the viscosity of mono, which is M2 here, is the lowest, which means that what takes place in aqueous solution is intramolecular association. So we decided this is a mono, there is no increase in viscosity. That tells us that what happened is mainly intramolecular association. Then we try the double tail. The double tail gives us a tremendous increase in viscosity, which is, this is the mono, and this is double tail. The viscosity is very high to the extent that the ratio is 1 to 3,905. Then we try the triple tail. The viscosity is also tremendously increased and the ratio is 105 centipoise, and the triple tail gave us almost 396,000. So which shows that it is nothing but intermolecular association, which leads to increase in dramatic viscosity. We also try viscosity as different shear rate, because the shear rate also affects viscosity, and this is a typical this is for without hydrophobe, this is with the mono, this is di, and this is what? Tri. And then we measure the intrinsic viscosity against concentration to determine the critical hydrophobic association concentration, and what is reported in the literature so far is around 1%, but we achieve, for triple tail, we achieve a critical hydrophobic association of 0.3%, which is a big achievement. And these polymers are pH responsive. We can have cationic what we have is cationic polymer. This cationic polymer can be converted to cationic acid salt, which is insoluble in water. But if you treat it with sodium hydroxide, we have ionic polyelectrolyte, which is water soluble, and we can determine the viscosity. We can also have variation of negative and positive. So we have polybutene and ionic polyelectrolyte. So this is a typical viscosity plot of anionic polyelectrolyte with increasing viscosity. And in conclusion, we were able to synthesize hydrophobic monomers with different degree of hydrophobicity. We have incorporated SO2 into our polymer to increase the solubility. And this work it involves a lot of interconversion, but we try to make the molecular weight as similar as possible because all the reactions were done at the same time to avoid the effect of initiator or temperature on our polymers. We also have achieved a critical hydrophobic association concentration of less than 1, which is 0.3%. And finally, we can have deuterion, where we have plus and minus on the hydrophobe just to check the effect of charge density on the polymer. And in the absence of micellar polymerization, we can also have hydrophobe using Butler polymerization by synthesizing a triple tail hydrophobe for the synthesis of diallyl monomer. And the use of this particular triple tail has indeed improved the properties in terms of association of the polymer. And lastly, I would like to thank you all for listening and my colleagues who work with me on this particular project. Thank you very much.
Thank you very much for a very interesting lecture, Dr. Umar. But unfortunately, we have no time to have questions. Maybe one short question. Okay.
Can I do?
Yeah, if you like. Okay. Very short.
Thank you first of all for your nice lectures.
Thank you.
I would like you to state your instructions by meta analysis, FTIR, and NMR, but you didn't do mass spectra.
Yes, usually mass spectra for polymers is very difficult because these are large molecules. We are talking about almost 300,000 molecular weights.
Yes, but you can do with mass spectra to get the exact molecular weight.
I think for
Defined by mass spectra,
I think so far, I think the best for associating polymers is MW. Associating polymers. MW is the absolute molecular weight you can get, the best. Then followed by MV, which is molecular viscosity. If it is possible, you can do MN, which is, you need GPC for that application. But for associating polymers, mass spec is not the best choice.
Okay, I think we should stop here. Thank you very much, Dr. Umar. We now move to lady's presentation. I hope she is ready.
Yes.
The presentation is from Saudi Arabia. Dr. Shadia Mahmoud Siri will present total phenolic content, total flavonoids, and free radical scavenging capacities of 2 local mean species. Would you please present your lecture?
Assalamu alaikum wa rahmatullah. This is Shadia Sirri from Taiba University. My presentation is about total phenolic content, total flavonoids, and free radical scavenging capacity of 2 local mint species. The aim of this work is to quantify total phenolic compound, total flavonoid, and free radical of two mint species. This species is Mensa longifile and Organum majorana. This is Mensa longifile is common name is Hasawi in Medina. This is used in folk medicine in Medina, and the Organum majorana name is Dosh. Mint is used as herbal tea, flavoring agent, and medicinal blend for carminative, digestive, stomachic, and antispasmodial in traditional medicine. This is rich with polyphenol compounds, and a large number of them well known as antioxidants. Oxidative stress is believed to be primary factor in various degenerative diseases. This is a characteristic by the presence of usually high concentration of toxic reactive species like oxygen and nitrogen free radicals. These free radicals, as example for these free radicals, sour oxide, hydroxyl, peroxyl, alkoxyl, hydroperoxyl, nitric oxide, and nitrogen dioxide radicals. These radicals and the other reactive species are produced in the body as a result of aerobic metabolism. The source of this oxidative stress is environmentally by UV or pollution or nitration or smoking cigarettes and so on. The plant oxidative stress can be caused through biotic and abiotic stress. Biotic stress from bacteria, fungi, or insects, mammazoids or mammals. And abiotic stress, according to alkalinity or salinity, UV stress. Accumulation of antioxidants compound in plant can be induced by abiotic and biotic stress. This antioxidant substance, as example of this antioxidant substance which produced in the plant to defense about stress, from stress, is vitamin C, ascorbic acid or glutathione, and so on. As example, another example of this antioxidant substance is phenolic compounds. These have great potential as antioxidant properties in prevention of various oxidative stress. There is highly positive relationship between total phenolic compound and antioxidant capacity. As example of phenolic compounds in the plants, this gallic acid, coumaric, caffeic. Phenolic act as antioxidants by several mechanisms, by donating hydrogen or from hydroxyl groups, which react with reactive oxygen and nitrogen and prevent formation of new radical and chain reaction. Interaction of hydroxyl group with pi electrons, or by the ability of phenolic compound to form chelate with metal involved in free radical formation. And flavonoids. This flavonoids is an example of antioxidant compounds which prevent free radical formation. As example of flavonoids, flavonol, catechin, flavonones, and isoflavones. The excellent antioxidant activity of this substance is related to the presence of hydroxyl group in position C3, 3' and 4' of the B ring. This gives high stability of the formed radical upon displacing electron and double bonds between C2, C3 of the ring C together with carbonyl group of C4. Methods. We can extract total phenolic or total flavonoids from mint plant by taking fresh leaves of these mints and grounded, extracted with methanol, shaking for 2 hours, and filtrate and analyzed. The method for determining total phenolic content in plant extract were determined using Folin Sucaltio. Folin Sucaltio is this reagent which form blue color with phenols like gallic acid. Gallic acid used as a standard for this determination. Total phenolic were expressed as microgram of gallic acid per gram of extract. This is named GAE or gallic acid content. And total flavonoid can be determined colorimetrically with aluminum chloride according to Ivanova. In the presence of sodium hydroxide, aluminum chloride in the presence of sodium hydroxide and sodium nitrite. Catechin was used as standard for these flavonoids. Free radical scavenging assay was used in measuring capacity of antioxidant as free radical scavenging. Diphenyl becryl hydrazine. This is the radical. This contains one electron free, which transfer upon all the molecule and form deep violet color. If there is an antioxidant which is scavenged this radical, the color was turned into yellow, from violet to yellow. The percentage of inhibition is as measured for the ability of this mint extract to work as antioxidants. The percentage of yield of methanolic extract of Hasawi is 1.6 and Dosh is 1.8. This yield is for Dosh more than for Hasawi. We can determine total, when we determine total phenolic content, spectrophotometric at 760 nanometer, the total phenolic were expressed as gallic acid equivalent by microgram per milli. This is a standard curve of gallic acid against gallic acid in the presence of Folin Ciocaltio. We measured the plant extract as measured of gallic acid content. This is the color. This is the color of antioxidants extract in the presence of Folin. The amount of total phenolic as a standard gallic acid equivalent per gram of extract is 7.85 and of those extract is 90.01. This indicates that Dosh contain more total phenolic content than Hasawi min extract. And total flavonoid content was measured as Katchen, using a Katchen standard at wavelength 510. This is the standard curve using spectrophotometric. This color is this is the color of antioxidant with aluminum chloride and sodium nitrite in the presence of sodium hydroxide, and the Katchen content in Hasawi extract was 22.7 and in Dosh 16.557. This is the color of extract with aluminum chloride. This indicates that Hasawi contain more more flavonoids than Dosh. And free radical scavenging activity is a measure of plant extract to work as antioxidant is measured by I50. I50 means the concentration of extract that decrease or inhibit the color of becryl hydrazine to 50%. This is the ability of Dosh extract is more than Hasawi extract. The ability of Dosh extract was 14.5, but the ability microgram per milli, but the ability of Hasawi was 23.5 microgram per milli. This indicates that Dosh need lower concentration to reach 50% of inhibition. Conclusion. Finally, according to this study, Mensa longophile, and organomajorano can be considered relative good source of natural antioxidants. And organomajorana, this is DOS, folk name is DOS, is more effective as free radical scavenging and antioxidant capacity than mensa longophile or hasawi, and those contain more total phenolic contain more total phenolic compound than hasawi, but less choline, but less flavonoid contents. This reference. Thank you.
Thank you very much, Dr. Mahmoud Shiri. We have maybe one short question, very short, please.
Okay, thank you very much, Dr. Shadia Sirri, Professor Kamal from Algeria. My question is very small. Is about how about have you compared your study with? You know that many papers are already published in Mind Spices. So have you a result that you compare that the phenolic compound are from Mind Spices grow in Medina is more rich than other grow in other world? And the second one,
Maybe
Please.
one is enough, please. Have you understood the question?
No. Can again?
Can you repeat in a
Repeat.
simple way, please?
have you compared your results of phenolic compound of manta species grow in Medina with other mount species grow in, for example, in Europe or in America?
No. I try to compare, but this other people extract by different methods. I can't do this comparison.
Thank you very much.
Okay, thank you very much again to Mahmoud Shiri. And we move to final presentation, which is from Algeria, Professor Nasser Belkacem Belbukhari. His presentation will be petrochemical investigation of aerial part of Limonia Strum Fei. Will you please present your lecture? He is not here? Oh. We could have given more time to the others if this was the case. Yeah, Dr. Mahmoud Shiri, are you there? There is one more question for you. Can you answer this question? Yes, please. Give the microphone there.
Assalamu alaikum. Yes.
Assalamu alaikum.
Alaikum salam.
I am Dr. Islam Khan from Government College University, Lahore, Pakistan.
Yes.
And actually, I myself have been involved in oxidative stress studies. And this type of studies is going to be very popular all over the world because of the growing trends in the diseases related with the oxidative stress. So I believe this is a very useful talk, and you have studied 2 plants from holy city of Medina as antioxidants. So it's not a question, but it's maybe some sort of suggestions. The one thing is that I think in near future, you can expand your studies by isolating the constituents, chemical constituents of these plants and identifying their structure.
Yes, this I think this is not my my current but I am analytical chemistry.
Okay, okay, good. Excellent. So you can, I think.
This is with me. This is Hind Babakar. This is from biochemistry.
No, that is from the organic side, and the procedure is very simple. You can advise some students to do the column chromatography before doing the TLC, so they will be able to isolate the constituent of these compounds, and they can be identified by using some spectroscopic techniques. That will add a very good value to these studies. This is the one suggestion.
Yes.
So as you are informing us that you are analytical chemist, so I think there are other indicators also. For example, ABTS assay, DMPD assay, and they could also be taken into account while studying the oxidative stress. So, and the results can be compared with the method, DMPD method, ABTS method. ABTS method is most reliable method. So we have modified this method quite recently, and it is reported. So this is another suggestion. And the third suggestion, you being an analytical chemist, actually in parallel, you can also develop new methodologies for determining the antioxidant activity or oxidative stress. So we have been doing that, and that gives a very high impact factor journal publications. Thank you very much indeed.
Thank you. I will do, inshallah.
Okay, thank you very much. We close the session. We thank to all speakers of this morning. Thank you.
Everyone, and thank you for being with us this afternoon. We are very pleased to welcome in this session Prof. Ramamurthy, Professor and J.C. Bose National Fellow at Department of Material Engineering, Indian Institute of Science, India. He is the editor of Acta Material and Scripta Material. He got his PhD from Brown University, and also he was a postdoc at UCSB and MIT. Okay, his research area focused on mechanical behavior of advanced material, with current focus on bulk metallic glasses, TIMG, and shape memory alloys, and organic crystal nano indentation technique. He awarded Shanti Swarb Bhan Tagar Prize, Engineering Science category, and Metallurgist of the Year, Metal Sciences category by Indian Institute of Metals and the Ministry of Steels, Government of India. He got a fellowship, DST, GOI, and he recently got a prize, TWAS, in the engineering science. Prof. Ram also is honorary professor at Jawaharlal Nehru Center for Advanced Scientific Research, Jakarta, India, and also in Jiang University in China and King Abdulaziz University. He supervised over 20 PhD students and 6 MSCC engineering and 22 ME students. He's co-authored for 200 papers in peer-reviewed international journals, which received more than 5,565 citations with an high index of 39 and average number of citations per paper at 28. So please join me to welcome Prof. Ram to give this lecture.
Thank you very much for this nice introduction, and good afternoon, everyone. It is indeed an honor and a great pleasure to be here in Jeddah, and I would like to thank Professor Asiri and his colleagues for inviting me over and organizing this very nice seminar. I just put it up just as a time space, but that is the administrative building of our institute in India, which is more than 100 years old. So I will be talking about nano indentation. So as the chair introduced you, I am a metallurgist. I'm an engineer who breaks things. I actually study how things break, and believe it or not, they are very important. It's important to study how things break. But recently we have been using, we are studying things which are very, very small volumes using this nano indentation technique. And in that process, we are able to connect with chemistry, and that is what is going to be my talk on. Okay, so just as an introductory thing, I thought I will put this up as a slide, and my story, this next 35 minutes is going to be about this. So what you see are two sets of bananas, and if I ask you which bananas are more ripe, which bananas should be consumed fast, you will say the one on the right side to you. So the bananas that are there are more ripe. This you can tell by looking at the color, right? Now, but on the other hand, I give you the same set of bananas, but I ask you to close your eyes before. And if I ask you to tell me which bananas are ripe, how would you do it? You will press and measure their hardness and say the bananas which are more softer are more ripe. Not only just bananas, if you are cooking rice, for example, if you want to check the rice is cooked or not, you basically press the rice and it is softer, pasta, anything. So if you want to bite something, you do this. So you do mechanical testing every day in your life without knowing. What you do here is a hardness measurement test in a qualitative sense, but what we will use this as a scientific tool to measure properties. Now, measuring mechanical properties is not a new field. It is a very old field. It's very important because when you want to design a car, an aeroplane, or a structure, steel structure, a bridge across the river, anything, you have to know their mechanical properties. And only then you will be able to design reliable structures. So we have been doing this for all metals, and we will continue to do this because it's absolutely critical. Now, the thing is, until about 20 years back, these are the kinds of instruments we used to use. We continue to use them. And so you need large specimens, big specimens that you can hold, and in kilograms at the least thing. So this machine that I show you here is about 100 kilonewton capacity. That is 10 power 5 newtons, just to give you a number. So please do remember that number just for a few minutes. Okay. Now, what has happened is in the last 20 years or so, there are these techniques that came up which essentially can now, when you measure something, when you poke the hardness of a material, you can now do it at load resolutions of 0.25 micronewtons. So that is 2.5 into 10 power minus 7 newtons. So we have gone from, this number, 10 power 5 newton capacity, to something like 2.5 to 10 power minus 7. So we are going very, very fine. Now, just to give you an idea, you may not have, what is a Newton force? So 1 Newton force is, suppose you take an apple, an average sized apple in your hand and drop it. The force it creates is the Newton. Okay? Actually, well, not quite, you have 5 apples, that is the Newton. So we are essentially now going 10 power minus 7 of that. So we use very, very tiny loads to poke at materials. Why is it important? And also, of course, we can measure the displacement, very high resolution. Why is this thing? So I told you here, if I want to test, I need large materials, large volumes of materials. I will say I need hundreds of kilos. But if I want to test really tiny, tiny materials that are available, this technique will be useful, and that is what I will demonstrate to you. Okay. So when you do indentation, the typical results are, what we do is we take a diamond tip and poke it into the specimen that we are looking at, and you get a response like this. You get a loading response, and then the material deforms plastically, and then you get an unloading response. And from these measurements, this is in some ways it's like a signature of an X-ray diffraction signature. You can actually figure out what the mechanical properties of the material are, hardness and elastic modulus of the material. And they will tell you about elastic resistance to elastic and plastic deformations. Now, the advantages are you don't need large specimens. You can actually test wherever you want, and this is copper wires made on a silicon substrate, and you can actually measure mechanical properties. Now, we use this technique to do a number of things. One of the first things that we did was to try to measure mechanical properties of nanocomposites, where we put nanomaterials, and this I will go quickly. So for example, one of the first ones we tried to do was, this is way back, silicon carbide and alumina nanowires. So these materials have very large surface to volume ratio. So as a result, you get phenomenal improvements. So here I just show you the elastic modulus as a function of volume fraction of the nanowires that we put in the polymer. So typically, you should not expect, because this is very dilute concentration, you should not expect. So this is what, a flat line is what is expected, but you see quite dramatic increase in the properties. This is because of the large surface to volume ratio. Now, that's not very exciting story, but you also can play around. Here I have 3 different forms of carbon that you have been discussing. So nanodiamonds, tubes, and graphene. Tubes are one-dimensional structures, whereas graphene is 2-dimensional structure. And nanodiamonds, diamonds, either you look at them as 3-dimensional or 0-dimensional, with point defects. So when you put these into a polymer, the way they interact with the polymers will be different. So you can think that the fibers will align along with the nanotubes, so you will have a different response than with nanodiamonds. So for example, if you put only graphene or nanodiamond, the increase is like this. It's quite significant. But what if you try to put 2 different things? Because now when you put graphene, it's a 2-dimensional surface, the polymer chains can attach it to it on a surface. Whereas if you put nanotubes, they can align along with the polymer chains. So if you put them together, would you get any synergy? So synergy means if I put 1 plus 1, if it is more than 2, that additional benefit is what we call synergy. Okay? So this is some work, again, somewhat old work, where we showed that these are for if you put only one material. For example, the blue is nanodiamonds, the green is few layer graphene. But if you put both of them together, you get an additional benefit, and that's what is plotted here. The extra benefit that you get. So if you put 1 plus 1, if it is 3, the additional 1 is what we get here. So what you will see is this is a logarithmic scale. So suppose if you put 0.4% graphene and 0.2% nanodiamonds, you will get an additional benefit of 400%. That's 4 times more than what you would get by just putting individual components. So this is quite dramatic enhancement in properties. So this is because of the interaction that happens and the different physical interactions that happen. Now, this is more recent. This is after listening to this morning talk on MOFs. For example, MOFs are very attractive functional properties because of the large pores they have, but they are also fragile. So, for example, can I now increase their mechanical properties so that I can deploy them in industry more easily? So we tried to put ZIF-8, which is a well-known MOF, with boron nitride nanosheets. And so the ZIF-8 is grown on boron nitride sheets like this. It's a schematic, and these are the kinds of things. This is ZIF-8 alone, but this is you could see this boron nitride sheet and ziphite particles. So we did these kinds of composites, and again, what we'll see, the functionality, this is uptake of nitrogen or carbon dioxide. The functionality is not lost. You get the same functionality, but at the same time, as you increase the boron nitride content, you could have pretty dramatic improvement in mechanical properties. So these are ways one can actually achieve mechanical integrity while your functionality is preserved, and this is possible. To measure those kinds of, is it possible or not, you can check it out with nano indentation technique. Okay, I'm switching gears slightly and going to talk about mechanical behavior of organic crystals, molecular crystals. So this is some 2-3 years back, we published this mini review where we try to connect nano indentation with crystal engineering. Crystal engineering is basically trying to use these principles to design various crystals, and nano indentation is a quite useful tool in this. So first thing we did was to look at saccharin, sugar. Okay, that's the first for fun kind of work, and we indented two phases of saccharin, 100 and 011, and right away, this is, by the way, this is the indentation response. You see there are significant differences. Let me again illustrate here. Okay, so if you indent on 1011, the indenter smoothly penetrates. You see this is a smooth curve, but when you indent on 100 surface of the saccharin crystal, what you will see is there are serration. It's not going in smoothly. It's so if you, this is more like putting a knife in a butter, whereas here something hard, so it goes in a jerky way. Okay, and what is interesting is when we look at this discrete displacement burst, what we call. So how much is the burst? How much is it, they're all multiples of 18 nanometers, 18, 36, 216, and so on and so forth. Why is that? First and foremost, these differences come about because when we indent on 011 phase, so we are indenting like this. And the slip planes, the planes over which molecules can slide past, not molecules per se, molecular planes can slide past, are at an angle. So they can nicely slide past each other without much of a difficulty. That's why you get a very smooth response. But if I, on the other hand, indent on 100, what happens is these slip planes are parallel to this. So these are slip planes, and this is perpendicular to the indentation. So they can't slip like that. So what happens is the stress builds up, and then all of a sudden they release the stress by sliding. So that is why you get these kinds of responses. Okay. Now we can actually explain it in terms of the kinds of bonding that is there, the kind of number of bonds, etc., etc. I will not go into those details, but so you can possibly measure this, and why this 18 nanometers. You can also do mechanics of it and explain this. Now, where does this become useful is where I'm going into. This is some work. So on odd-even effect on the elastic moduli of carboxylic acids. So all of you know these acids, the diacids, show this odd-even alterations in melting point. So if you have even number of carbon atoms, that is 2 or 4 or 6, you have high melting point. And if you have odd number of carbon atoms, you have low melting point. This is a work that Adolf von Baeyer has done in 1877. Okay, and I was told that this is the first thing that they teach in organic chemistry. Now, a number of, not just those diacids, a number of other acids also show this odd-even alteration. Now, there are lots of different theories that as to why this occurs. Conventional wisdom is that the density variation is what causes them. So, but then there was this paper in JACS. They say that density variation is not the reason. It's not the density that you have this. But this is because when you pack these things, the strained intermolecular geometry of the odd acids. Okay, now what do I mean by that? So if you look at the the chains in the even one, C4 or C6 or C8, they're all planar. Okay? On the other hand, if you look at these odd ones, C3, 5, 7, 9, you see these extra bonds sticking out. So the way I would like you to visualize, suppose if you are traveling, if your all clothes are ironed nicely, you can pack them very easily, right? On the other hand, if they are not ironed, they're all crumpled and whatnot, you can still pack those clothes in the suitcase, but you have to really push them very hard. So the odd ones are like that. So you have to really strain them to put it in the matrix. Now why that reflects in melting point alteration is because when you have this, there is already strain, so they melt readily. Now, I am a metallurgist, as I told you earlier, so we know very well that for a given crystal structure, the melting point and elastic modulus are correlated linearly. This is because they both depend on the same factors, namely crystal structure and intermolecular interactions, atomic bonding. That is, so now, if I then do this, examine this, is elastic modulus also varies the same way, and this is the thing, elastic modulus as the function of number of atoms. You can see that when it is odd, it's low, and it's even, you get high. So you get exactly the same alteration in the alternation in the melting point, elastic modulus, just as you would get, this is melting point, so you could see that they exactly vary in the same way. And in fact, if you cross plot them, elastic modulus and melting point, you get almost a linear response. So this is known, this is not very, but what it proves is this, the idea that strained intermolecular geometry, which was only theoretical idea before, this confirms that. And I can send you the paper as to why that is, the details of that. And we also further show, for example, these are now the normalized specific modulus. So I normalize elastic modulus that I measure with density, and you can see you still have the variation. So it is not the density that is causing this. This is because when you pack these molecules, you are straining them, and that is why these properties are changing this way. Okay? So you get physical insights into these kinds of chemical phenomena. Now, we take it a little more further because until now we are just doing it for fun, so to speak. Can we really get into some problems? So one of the issues is aspirin's polymorphism. Aspirin, many of us would have taken when we have a headache or something else. And aspirin, people used to believe that there is only one crystal structure of aspirin. And then some people else came and said, no, there is a polymorph of aspirin. There is a form 2 of aspirin. And in fact, we published that work, and then Nature Chemistry has actually commented saying that aspirin headache was solved by us. So aspirin, just to give you, it's 40,000 tons of aspirin is consumed every year. And let me give you context of why we are doing this. See, most of the times when you take medicines, you take them in the solid state. You prefer to take them in the solid state because liquids measure quantity that you take, the stability issues, everything. And so you take a formulated product either as a tablet or a capsule or so on and so forth. And when you take it in solid form, it's in a crystal structure. So the crystal structure properties, the crystal's properties are also important. So suppose if you are worried about biodissolubility, this becomes very important because the crystal structure will tell you how fast it will dissolve or how slowly it will dissolve. So the properties are, of course, depend on the crystal structure, and polymorphism I don't need to introduce to chemists. That you can have the same material in 2 different forms, and we have already looked at carbon forms, diamond and graphene and so on and so forth. So in the case of aspirin, this just gives you the idea that there is predictably elusive form of aspirin. They were able to predict it, but they didn't find it. And this is actually Zoratko that has done this work. And so there was a question whether there is form 2 or not. And the reason is X-ray always didn't really resolve this. I will tell you why it is. For example, you do sometimes see form 2 peaks and sometimes you don't see them. Okay, and let me just give you the structure. So if you take the color code is form 1 for red. So these molecules are arranged this way. The unit cell is this. And now if I take this and shear it by half of this C, the unit cell dimension C, I get form 2. Okay, so and that is the crystal structure. So it's really, they're very closely related, but one is shear related to another. You're shearing the part of crystal with respect to the other, form 2. Okay, and you can actually write down what the relationship is through a matrix form. Okay, and so now when we took these two different forms, initially there was a lot of confusion amongst our results, and I will tell you just in a minute why that happened. So when we indented along this axis, okay, a parallel, so this is roughly the crystal structure, and we are indenting like this. So if I indent on 100 phase of 1, that is like this, I get this very distinct response, serrated response, and also very hard response. But if I, on the other hand, if I take form 2 crystal and indent again along this direction on 100 phase, I get a very different, very smooth. The thing is smooth and also penetrates a lot more. That means it's much softer. And the mechanical properties also tell you that. Okay. Now, you get very distinct responses depending on this. Now, why is this happening? You can explain it, but one way to just think it is when I apply force, this is that form 2 that is sheared like this, it just goes back to form 1. Okay, that is what is happening. If I apply a load, which is like this, it just goes back to form 1. Okay, now the explanations are here and all that. Now, just how do I confirm it? So what we did was we took form 2 crystals, then did X-ray diffraction. So this is the X-ray diffraction, and you see these extra peaks that are associated with form 2, and then we ground them, mortar and this thing, and we ground them and then did X-ray, and the form 2 has become form 1. So when we apply mechanical forces, form 2 has become form 1, just as the nano-indentation response predicted. So the polymorph phase transformation associated with mechanical stress, we can actually figure it out with respect to using nano-indentation. Now, you do that kind of mechanical operations. Don't think it's only academic exercise. So when in pharma industry, then when they grow these crystals in highly controlled conditions, they do afterwards milling and grinding and tableting. All these are mechanical operations. So if there are possible phase transformations, it could be a issue, and these kinds of things, studies will tell you this. Now, when we actually initially tried out, we had all confusing results. Subsequently, we figured out, because there is this intergrowth polymorphism. That means form 2 and form 1, what we thought were form 2 crystals, actually had domains of form 1. Okay? And when we indent on those domains, we are getting different response. So for example, if I indent on form 1 domain, I get this response, and if I get in this domain, I get completely different response. So if there is quote unquote a microstructure, there are these form 1 and 2 are different polymorphs are intergrowing, because remember the energy level, the energies that the formation energies are not very different. So you could have this intergrowth polymorphism, and you will not be able to pick it up with any other technique, because the kind of resolution I have, spatial resolution I can get in this is very high. Okay. Now, this is where these are microstructures of metals, various metals that you actually use without your knowledge. But you could see this, right? Because we polish them, etch them, and you can put it under a microscope, and you can see the different kinds of microstructures. But when it comes to organic crystals, you don't have this luxury. You can't polish them, and you can't put in microscope and say that. So if there is intergrowth polymorphism or a second phase, a microstructure to the material, how will you know it? One is, of course, X-ray, but the thing is, if the domain size is smaller than your focal diameter, you will not be able to pick it up. Okay? Now, this is where, again, I bring the bananas. Some of you have missed this earlier. So, what I'm trying to say is, if you can look at it, like the microstructures of metals I showed you, you can tell there is a microstructure. But if you can't look at it, suppose your eyes are closed, you can figure it out by pressing it. Which one is that? So, if I have a microstructure to the organic crystals, I can figure it out because I can't see them, right? I can't put it under a microscope and get the domains. But I can poke it and say, here it's soft, here it's hard. There is a distinct difference. Okay, so what did we do? So the aspirin was actually accidental work. We didn't really set out to do it. So then we looked at another important medicine, felidipine, which is again extensively used. Here again you get these kinds of polymorphs. This is work done with Andrew Bond, who used to be at Copenhagen, but he moved to Cambridge. So again, in this case, for those crystallographers, if you are interested, this is the kind of form you can have. So you could have one material, form 1, where the crystal structure is like this, but you could also have a form 2 where the cell B, you could see that it's sheared, right? It's like this, and I sheared it, okay? Now, so this is a control experiment we have done subsequently. So we said, okay, so in this case just again, I am fond of food, you could see this. So now, if I go back here, if I indent from the top, if I poke the material from the top, I will not be able to tell the difference between this crystal structure and this crystal structure because it's exactly the same. Only when I indent from the side, I will be able to differentiate. So if this is like, strawberry cheesecake. So if you are looking, you know that it is a layered structure. There is soft layers and also relatively hard layers. If I poke from the top, I will not know that there is actually a layer structure, right? Only if I poke from the side, I will know this. All right. So first thing to do is to indent from the top. This is the direction we are indenting, and we get same response with some stochastic variability, some statistics, but that is the response you get. Now, let us try to poke it from the side, okay? Because when you are poking from the side, by the way, they're all crystallographically equivalent here. So you can see that there are two different materials, and this is blind experiment, right? We just do these experiments hundreds of times, and you can see from this load in depth curve, I have, here it's very clear, right? So I get two distinct responses. They essentially partition themselves into very clear two bins of response. And just to illustrate that, I plot hardness versus modulus. So there's one group here, one group here. And there are some points in between which probably are at the interface of these domains. So this experiment right away tells me that, if I didn't have that, there is actually a microstructure to the material. All right. There are two different domains, one which has high hardness and modulus, one which has low modulus and hardness. So at a much finer resolution. So this is what we actually, we anticipated it and we saw this. So this allows us to essentially examine the microstructure of material. This is published in Angevente Chemie this year or last year. Okay. Now, this essentially helps you also, so the 2011 was the year of chemistry, and there are a number of problems that there was an overview on getting physical to fix pharma industry. There are lots of problems because the failure rates are very high, and they say that material science approaches are needed, and this is the kind of approach you could take. Of course, this doesn't solve every problem, but it can help in many ways. And now we subsequently, I think my time, how much time? 5 more minutes. So, so far we have shown that nanoindentation can actually be used to study organic crystals, polymorphism, whether there is an intergrowth polymorphism or microstructures. We subsequently started looking at whether we can correlate the solubility and hardness. The reason is solubility is very important. If you take a drug, it has to be dissolved in your in the system so that it's medicinally useful. Otherwise, it's not. So we check the curcumin and sulfathiazole, and we actually see that the solubility correlates very well with hardness. So this is a useful parameter because hardness is somewhat something that you can measure straight away. And as we say, softer is more soluble. So the material that is easy to digest. So more softer it is, more easy to digest. And we also have done further thing about whether if many drugs can lose water as you store them. That's why if you have there is a shelf life. When you buy, you see when is it manufactured, when it is expired, and after that you don't want to use that medicine. So same way, we can also keep monitoring the mechanical properties and in the process tell whether there is water loss. This is what we did with sodium saccharinate. I'll skip those. And more recently, we have been also looking at co-crystals and things like that. Can we design, now having understood mechanical properties, can we design harder materials? Of course, yes, you can do that. This work is published in Molecular Pharmaceuticals, and where we have co-crystals approach and salts approach, and because this is voriconazole is a very important drug, but it's very soft. If it is too soft, again, you can't use it to make products because grinding is a big problem. It's too soft, it's gooey. And I will skip this because I'm running out of time, and I have, so now this is some 6 months back we have done this work. So we, over the period of doing this, we learned a lot of principles as to which kind of thing gives me stiffer structures, which kind of things, which kind of molecular interactions give me softer structures. So can we then turn it around and learn some of the things? So for example, what are the crystal engineering design principles for getting highly elastic organic crystals? So we did this by looking at these series of molecules and the crystals of them. And for example, if you take one of those crystals, this is a needle-like crystal, and you can see that these are snapshots. I have also movies, but you can flex them a lot. Okay, so these are sort of things that you can do qualitatively, but nano indentation gives me quantitative data, and we use that in a different setup to show that it is indeed the possible. And on the basis of this is the summary of that particular work. If you want a highly flexible material, how do you get it? So the way to do it is basically have a lot of molecular things which are easy to break, multitude of intermolecular interactions, weak intermolecular interactions which are easy to break, but if they break readily and slide a lot, long distance, you will not be able to recover. So they also have to have this zigzag. You see this zigzag structure so that they lock, they don't migrate long distances. So these are the kinds of things that are essential if you want to design highly flexible molecular materials or organic materials. So this is the schematically illustrated. You need this kind of zigzag structure so that you can bend it very easily, but it will recover back on releasing the load. Now, this is again a JAX communication that came up this year, where you also, if you want to alternate, if you want to design or engineer material with higher hardness, how do you do it? As a metallurgist, we know this very well. We have been doing this for millennia, where we alloy it and try to do this. So, for example, that is called solid solution strengthening in metals. It's very widely studied, well-known, well-used technique. Can we do this for organic materials now? So, in this case, we play again with a very important medicine, omeprazole, active pharmaceutical ingredient, where we take, it's a tautomeric compound with tautomer 1 and 2, where we vary tautomer 1 systematically, and you can show that hardness varies like this. Now, these are the crystal structures. It's more schematically illustrated here. So if you have form 1, when I indent, it can slide past like this, and that's why it's soft. Excuse me. So it's soft here. But as I put this form T2, tautomer 2, which is sort of twisted, you see this molecule here is on, both of them are one side, whereas here it's turned around. So, so it is essentially like this now. If I put more and more of form 2, what happens is these extra things will prevent these molecular layers from sliding past each other relatively more, make it more difficult. And that's why you get higher and higher hardness. So you can actually, this is like solid solution strengthening because it's still omeprazole molecule. You can use it, but you can keep putting more and more so that you can tune the hardness as much as you want. So the idea is the principles that you used in a different discipline of engineering, metallurgy, you can also use them to tune mechanical properties the way you want, so that you can then get more formulation-wise, it's easier to formulate these products and so on and so forth. So let me summarize because my time is up. So what I have shown you is there is this technique, which is what nano indentation technique, which essentially can measure properties of really small volumes of materials. So this would not have been possible some 20 years back because the crystals my colleagues grow are very tiny and I would not have been able to test them. But now with the advent of this technique, I can actually measure their properties, and inter alia, because these are physical properties. And when you measure some physical properties, you can always look at the structure because the property reflects the structure property correlations, as we say. And we can also understand and turn it around and design better and materials or for whatever functionality, we can design it for whatever use, manufacturing, etc., etc. So this technique allows us to do that. And in the process, a metallurgist like me, an engineer, to give a talk in presence of chemists like you. Because now with this interdisciplinarity, we all are same. It doesn't matter whether you're a chemist or physicist or an engineer, you can now do across the disciplines, you can do wonderful, interesting science. Thank you very much.
Okay, thanks, Professor Morty. And we open time now for questions, for a few questions. So if you have questions, please raise your hand.
Yes, please go ahead.
Thank you very much. Very interesting and very, I would call it integrated kind of a lecture. Two questions. One is related to the two forms of aspirin, form A and form B. Did you see any changes in the drug efficacy in form A and form B?
We didn't measure the drug efficacy per se, but form B, which is higher energy form, is also softer and subsequently not for that particular material. We show that the softer form is more soluble. So naturally, if I extend that,
that means absorption on the level of absorption. It's
be
certainly.
Yeah. So this is particularly true for curcumin, the one.
That is my second question. Yeah. How come the three curcumin forms have different colors?
Okay, now
any changes in the chromophoric level?
They're different crystal structures, and that's probably the reason. I don't know. This is not my domain.
Because I'm fascinated by the three colors. Yeah. One is the pure
yellow,
yellow or orange color. The other ones are towards red.
Yeah. So curcumin 2 is, in fact, that is the major problem. It's supposed to have a lot of medicinal value, but its biosolubility is a big problem. The curcumin, you cannot use it. That's why. So tablet form is not there. So if you can find, and it's patented by the inventor, not us, and so this, then you can use it as a tablet and get advantage of the medicinal benefits of the curcumin. This is turmeric, for your information.
Right. Because curcumin is becoming very fastly growing anti-cancer.
It has also anti-cancer properties.
For a dozen different cancers. Thank you.
Yeah, you can shout it.
Yeah, I can shout. What's the smallest size of a single crystal that we could
Okay, the smallest size in principle is 10 microns or so, or even that. The only constraint that comes is when I indent it, I would like to hold it firmly, because you see the displacements and the that I measure are very tiny. So there are other, so if you can give me a molecule or a crystal that is embedded in something which is firmly held, I can indent it, no problem. Then 10 microns is a lot.
And to build on that, so you guys could align it in whichever direction you want.
Yeah, exactly.
So if you have X, Y, and Z, you could really see the indentation on all these X's.
Most of the times we do on major facets. So my colleagues or my joint students would do face indexing before and after to make sure that we are indenting on the same face.
Thank you.
And so that's why we don't indent on all the faces, because some faces are not accessible. You need to hold them also somewhat firmly when you indent.
Yeah. My question is, how did you fix your organic crystal on the because you need a very flat surface for the nano indentation measurement?
This is a very good question again. So what we do is we take some sort of epoxy that won't react with the organic crystal, and you can gently press it so that it's flat. So I need a flat surface. That is another requirement. And so by the way, we do a lot of things which I didn't go through. We scan it, make sure it's flat, we clean it, and so on and so forth, and then only indent. So we know how to do it very carefully. In fact, we have extended it to higher temperature indentations in the recent past.
So basically it's the same as like we're doing AFM.
Exactly, yeah. So but AFM is an imaging technique. It's not an indentation technique. So its purpose is altogether different. It's only for imaging. Although some people use this as indentation, it's not quite right.
Okay, thank you. We move on second speaker, and it's our pleasure to have Professor Abdullah Asiri from Saudi Arabia, and he's going to talk about synthesis and use of photochromic compounds as a smart switchable glazing for solar energy and daylight control in building.
Okay. It gives me great pleasure to present this talk to such eminent professors today, and I apologize in advance for any problem preparing this presentation. I prepared this presentation just last night very quickly. So the title of this talk is Synthesis and Use of Photochromic Compounds as Smart Switchable Glazing for Solar Energy and Daylight Control in Buildings. The outline of this talk is going to be the definition of chromism and photochromism, type of organic photochromic molecules, Folgide structure and synthesis, photochromism of Folgides in different polymeric matrices, the effect of additives and photochromic properties of Folgide and polymeric matrices. And also we will talk about photochromism of spiropyran, polymethyl methacrylate, and epoxy thin films. Photochromism of spiropyran, polymethyl methacrylate, and epoxy thin film in the presence of UV absorption. Definition of chromism. The chromism is a phenomenon that where we have a material which can change the color from colorless to much more color due to application of external stimulus. Many materials are chromic, including organic or inorganic material and conducting polymers. And the property can result from many different mechanisms. So if you have a compound in the state in state A, then you can apply external stimulus to it, either pressure or heat or light. Then this compound can transfer to another form, which B forms. This B form now have a different absorption spectra, so the color is different from the original one. And the original one can revert back to the colored one can revert back to the originals when you apply another kind of external effect. Photochromism is one part of the chromism phenomena. So in the photochromism, this phenomena is forced to happen by applying external light. Sometimes the compound is colorless, it goes to deeper color. For example, if you have this compound A is yellow or absorbed in the UV region, then this compound, when it's absorbed the UV light, it can go to give you a colored compound in the visible region or even in the infrared region. This form B now can revert back to the form A when we apply a light in the area that this compound absorbs. By tuning the structure, we can get a variety of color of the chromic material, so we can have a color changing from yellow to the far end of the visible absorption, so we have different colors. Families of organic photochromic compounds there are many families of these photochromic compounds. The first family is the spiropyran, which discovered back in the air maybe in 1996 or something, 1969. And then spiroxazine, chromine, and fulgamide, diarylethylene, spirodihydroindolazine, and azo compound, polycyclic aromatic compounds, enals, polycyclic quinones, and pyrimidine, spirocyclohexadienone, phylogene, triaryl methane. The family that I will talk about is the Folgides and spiropyran. Folgides are nice compounds, have this formula on the right hand side. Folgide is a Latin word which came from fulgere, which means shine, because these compounds usually crystallize as a shining crystals. Synthesis of Folgide. The Folgide can be synthesized through these routes, which is a multi-step synthesis starting from ketones, then condensation through Stauby condensation with the diethyl succinate in the presence of base such as tertiary butyl oxide. Then we will get the half ester. This half ester, then to activate the other methylene, we have to re-esterify it, And then the diester again goes through another Stobie condensation using aldehyde or ketone, whatever is needed. And then we get the half ester again, then hydrolysis of the half ester, we get the diacid, and then dehydration of the diacid, we get the fulgide. This is the form of the fulgide on the left-hand side here. By varying the aldehyde and ketone, we can get varieties of fulgide. For example, this compound here can be produced by condensation of dicyclopropyl ketone with the succinic diethyl succinate, and then followed by condensation of 3-acetyl furan or thiophene derivatives. Then we can get the fulgide, which goes under these photochemical reactions. The Z4, the one on the left-hand side, is the Z4. Excuse me for this. This color on the left hand, the Z form and the E form, are yellow in color. Then when they get more light, they cyclize to give us a red color of the cyclized form of the fulgide. The cyclized form, when irradiated with the white light, it goes back to the E form. Derivative of fulgide are the fulgamides, which are the amide derivative, can be produced by reacting the fulgide with different amines. And fulgamide are also photochromic. We'll talk about the photochromic properties of one of the fulgides in a polymeric material, in polyurethane. So we can produce a coating which can be used to coat a glasses of the building, so we can get a color, a glass which is coated with a photochromic materials, which when exposed to the daylight can get darker, and then in the evening it goes back to a clear glass. This is the UV spectrum, or the photochromic performance of the polymer polyurethane doped with the suitable amount of this fulgide. We can see that in the beginning, the absorption is only in the UV region, and then by increasing the radiation with time, there is a development of a new band at 500 nanometers. This band is responsible for the formation of the color, the closed form of the reactions. So also this one can be reverted back completely to the E form, which is colorless, by radiation or by taking off the source of the UV light or irradiating with the white light. So this is the photochromic behavior which happens if we have glasses coated with this polyurethane coating. The other one is the bleaching. The left-hand side is the coloration, the other one is bleaching. So we can see that when bleaching, the compound goes back nearly to 95% to the original one. Of course, for applications, we have to have a good performance of this photochromic material. So the coloration reaction should be fast, and the discoloration also should be fast. So we try to optimize some conditions to see how can we study the effect of temperature, and also studying the effect of some changing the polymeric matrices. And this table shows some result for the kinetic of these photochromic reactions, the coloration and the bleaching. This figure shows the fatigue. The fatigue is the definition that used to explain the ability or the stability of the photochromic compounds against the cycling, discoloration cycle. So this compound in the first figure, we can see that the compound is stable after 11 cycles from coloration and discoloration at 25 and also at 80 degrees Celsius. And this is in polyacrylic acid. This is the fatigue studies. The effect of additives. Of course, the most serious problem for these photochromic compounds, which hinder them maybe from commercial application, is the photostability. Most of the compounds cannot survive for a long time in the sun or in the direct contact with the UV light. So most of them get some, what do you call it? They are unstable against this light, so they just decompose. So what we thought if we can get some UV stabilized to the polymeric matrices, maybe we can maximize the fatigue of this compound. So we use this Unifol, which is a commercially available UV absorber used in the polymeric industry. And this is the photocoloration in the presence of this Unifol. And this is the discoloration. And let us see the fatigue. This is the half-life table and the rate constants for this photocoloration, discoloration process at different temperature in different polymeric matrices in the presence of UV absorber and the absence of UV absorber. We studied another fall guide, which this admin derivatives. This compound, because the long conjugations colored from yellow to deep red, deep yellow, deep blue, or deep green color according to the alkyl group pendant on the left-hand side. So you can see that we shifted the maximum absorption of the closed form to about 600 nanometers. And of course, these kind of compounds, because they are shifted a little bit further to the far end of the visible region and maybe in the near infrared region, have some application in the optical data storage at that time when we prepare such compounds. And this compound can find good applications in the optical data storage using the laser that emits light in that region. I have 2 minutes? Okay. This table shows the half-life and the rate constant for the coloration, discoloration of this fall guide in different polymeric materials, and also in toluene solution for comparison. In 1993, I think, when I was doing my PhD at Cardiff University, most of the people in the world was trying to shift the maximum absorption of fall guide to further beyond 600 nanometer of the cyclized form. And one of the attempts actually we did at that time is to condense the fall guide with the malonyl nitrile in the presence of moderate base, then cyclize again. Unfortunately, we were able to actually isolate this compound. This compound now, when it colors, it gives us a compound absorbing beyond 630 nanometers, which is the little bit with a tail in the infrared region. So that was really breakthrough at that time, because most of the people in the past used to prepare fall guides and compounds which absorb at about 500 nanometers. This is the UV-vis absorption of this compound, which doesn't look very nice because the polymer matrix here has a lot of effect on it. This is some kinetic data in polymethyl methacrylate. I still need 2 more minutes. This is the spirobiran compound. Spirobiran compounds absorbs at 500, at something like 550. This compound, especially in particular, when irradiated with UV light. And this is the bleaching of this compound. This is the tables for the photophysical properties, rate constants. And also we studied the effect of the UV absorber on this reaction. And this is the table for the rate constants. Conclusion, photochromism performance of fulgide, spiroxazine, spirobaran affected greatly by changing the polymer matrices. Annealing of the polymer photochromic thin films did not show any loss of the photochromic material. Improvements of the photochromic performance was observed upon annealing. The resistance of fatigue studies photochromic compounds are highly improved by introducing of the UV absorber. More investigation are still needed to establish the mechanism of interactions between the UV absorbers and the photochromic compound. This is acknowledgement for some of the people who work with us in this work and some of our financial supporter. And this shows us what we were thinking of. If you have a window of glasses, you can coat it with these photochromic materials. When the sun hit these glasses, it can color these glasses by different color according to the compounds that we used. And then in the evening, you can go back to the original color. Thank you very much for your attention.
Thanks, Professor Asiri, for an interesting topic. And now we leave time for a few questions.
Here.
Okay, please.
The half-life is a few minutes, I saw. You know, the maximum is something like 55 minutes in one of the compounds.
Yes.
What is the expected half-life for real deployment of these materials?
Well, the shorter the half-life is, the better, actually. Spiroxazine is a good candidate because the half-life of the coloration is short and much more shorter for the bleaching reactions.
Okay.
So the spiroxazine are very good, but due to difficulties in preparation of spiroxazine, the commercialization is still.
The other thing is you showed that fatigue results. The compound, the second one, actually improved with time, temperature.
Yes.
That's the
the
fatigue.
Because this is actually all due to the polymeric matrices. So once we hit or anneal at 80 degrees, maybe there is some cross-linking of the polymers, so that the material is get inside with the light going to the materials, find it difficult, so the compound did not decompose. Maybe this is one of the mechanisms. Steve.
Very interesting results. I'm wondering if you put pressure on these polymer matrices, do you observe any piezochromism, so pressure-dependent color change?
Very good question.
That would be detectors for mechanical devices like airplane, models, surface currents, and stuff like this?
Well, you ask a very important question. Not for this one, but I will tell you the story. Professor Stephen is asking about what happens if we apply a pressure to this polymeric material. Does the color change or not? If it changes, it gives you a good sensor for mechanical testing. This is for this photochromic material. We tried several times for the crystal itself before we dope it to the polymers. It did not give change in the color. So in the polymeric material, actually, we did not test it, but I will tell you a new compound which we discovered also in my PhD called tribochromic compounds. Tribo means pressure. This is a word means pressure. And these tribochromic compounds are crystalline material with almost color or to very, very faint color, colorless to faint color. And when you apply a pressure, even with the spatula, very short, small pressure on it, they go in different colors. So that compounds could go from yellow to deep red. Yeah, and that was fortunate for me to complete all my PhD on that field, which is the tribochromic compounds, and we got a very nice results. Also, we had a very nice patent on that one. And these compounds still we are playing with them, and we try to improve many properties of these. This is called the tribochromism. We introduced this term for the first time because in the past there was something called piezochromism. Piezo also means pressure, but the difference between the piezochromism and the tribochromism is that the piezochromism, when you apply the pressure to them, okay, they reverts back to, if you remove the pressure, they reverts back to the original. But our compounds, when you leave the pressure, put the pressure, they get colored, but once you remove the pressure, the color is still there. And this is important, because the difference between that one and this one is for the application. If you need something, for example, to authenticate something, for example, if you have a check, you can put a material of this kind, and then for the authentication, you could just have a way that you can press the pressure, and then this material, you prove it's genuine, and the scar that you will have will not be removed. Also in photocopying, if you have a security document, then you can put a material, this material to these security documents. Then if somebody photocopy it, the heat of the color also can give you color which never moved. So you will know that this document has been photocopied. More questions?
More questions? Okay, we move. Okay, thanks, Professor. We move to the last speaker is from Morocco, Dr. Sana Majid. She is going to give a talk entitled Technique of Membrane Processors, the Directed Process of Facilitated Extraction and Recovery of Cholesterol from Food Products.